Hello, everyone. Welcome to session 4. My name is Yuchen Mansouri, and I'm chairing this session. And so we're going to start with the first paper, Multirobot Learning and Coverage of Unknown Spatial Fields. And the presenter will be María Santos.
Okay, great. Thank you. All right. Hello, everyone. Good morning. My name is María Santos, and I'm going to present today the paper Multirobot Learning and Coverage of Unknown Spatial Fields. And before I dive into the technical content of the presentation, I would just like to thank the organizers for being able to do this hybrid conference. I've seen some pictures of the venue and everything in Cambridge, and it looks lovely. And I just wanted to let you know that I'm really, really jealous. I couldn't make it there, but I hope everybody's having a great time. So with that, in this paper, we study the problem of coverage in the sense of how to distribute teams of robots in a domain in order to optimize the monitoring of the environmental features in that domain. Here we see two examples of a team of 10 robots moving within a domain D and obtaining spatial allocations that try to optimize the surveillance of these environmental features that are depicted here as higher shades of yellow. And before I present the technical contribution of this paper, I would like to introduce some notation that will become handy as we advance through the presentation. So we pose the the coverage problem within domain D, where the environmental features are encoded as a density function phi of Q. And we have a team of N robots with positions F sub I, where the bold letters are going to denote the stack position of these robots that are to move in this environment to optimally cover this domain with respect to phi. A typical approach to do so is to divide responsibilities among the different agents in the domain, such that each robot I is going to be in charge of those points. So obtaining a Voronoi partition of the domain. And this partition allows us to write the collective locational cost for the coverage problem, where each robot I is gonna evaluate within its Voronoi cell how well it's doing by weighting each point Q by how far this point is and how important this point is to the coverage problem. Summing over all the agents lets us obtain this collective locational cost with a lower cost corresponding to a better coverage of the domain. And to minimize it,
we can't hear you, just there's a technical problem here, or probably there. Can you hear us, Mike? Still no sound.
Can you hear me now?
Yes, yeah.
Okay, thank you. Should I continue from here or should I go back?
You start from cost, basically. Yeah.
Oh, okay, perfect. Sounds good. Okay. Thank you for letting me know. All right, so we're there. So I was saying that in the cost, we're letting each robot evaluate over the Voronoi cell how good the robot is doing by weighting each point by how far it is and how important the point is. And we're going to have a good coverage of the domain when we're minimizing this cost. Following the direction of descent, we get Lloyd's algorithm, where each robot is going to head towards the center of mass of its Voronoi cell. In this paper, we're concerned with the problem of how can we perform this coverage task when the density function phi is initially unknown to the robot. So a common assumption in this type of algorithms is that we have information about the distribution of features over the domain, but that may not be the case. In this paper, we proposed an exploration-exploitation strategy where the robots are gonna simultaneously perform learning of the density function over the domain and also coverage of this density function. Thus, learning corresponds to the exploration part, refining the estimation of this density function, and covering with the exploitation part, optimally covering it. We use this algorithm, prediction correction coverage, PCC, as a baseline, which exploits the structure of the cost that I was commenting before. But now, because we don't have prior information about phi, what we use instead is a surrogate function of the density function. This surrogate function is modeled as a Gaussian process with mean mu and covariance k and hyperparameters rho and tau. And as the robots are going to move throughout the domain, they're going to take noisy samples of the actual density function phi, and we're going to denote these samples as y. The new samples are going to be used to update the hyperparameters, and these hyperparameters are going to be used in each iteration of the algorithm to build the surrogate function. However, in the PCC algorithm, we have two separate roles for the robots that explore, thus perform coverage, and that exploits, minimize the uncertainty over the domain. In particular, we have n-1 robots moving around the domain according to Lloyd's algorithm calculated with respect to the surrogate function. And then there's a single robot that what it does is that it samples those points in the domain that maximize uncertainty. Instead, in this paper, we propose for for all the robots to be simultaneously performing these explore-exploit strategies. So we present two different sampling strategies for choosing these endpoints with maximal uncertainty. And having those points in hand, we can make the robots move towards the location that weights the points with maximal uncertainty, thus exploring, and the points that corresponds to the centers of mass of the calculated with respect to the surrogate function at each point. And these are weighted by a decreasing sequence that at the beginning favors the explore task. And as we advance throughout and we get better estimation of the density function, we're going to favor more the exploitation part of the algorithm. Here we have a video that, showing how this works. On the left is the actual density function that exists in the domain, and on the right we have at the top the coverage task, where we see the robots depicted as black circles that move over the domain and take samples denoted by the red X's. As the robots take more and more samples over their domain, the surrogate of the function is being refined. At the bottom, we can observe the two different strategies for sampling the points that maximize uncertainty. In the case of the look ahead is a centralized search, where we are sequentially looking for these points over the domain, where in the case of the Voronoi estimation coverage, the robots are constrained to pick these points within their Voronoi cell, thus working towards the decentralization of the algorithm. We offer theoretical guarantees about the asymptotic no regret obtained with these algorithms. If we define the regret as the difference between the locational cost that we're obtaining with respect to the actual density function with the locations that we're attaining by the robots, minus the cost that we would have, so the optimal cost that we would have if we actually had information about the phi, then we can bound the cumulative regret of the algorithm sublinearly, where the terms that are inside the square roots eta depends on the size of the domain and the noise of the samples that we're taking over the domain. Big N is the number of robots, as we said before. T is the time horizon, Beta is a non-increasing sequence that appears in the surrogate function phi of t, and chi of t is corresponds to a term that denotes the information gain that we're getting as we take samples over the domain. We present simulation results where we compare the performance of these two algorithms with respect to the existing literature. This is the, in this case, we run several examples, but I'm showing just one of them. This is the real density function, and we can see how as we perform several iterations, the regret goes to 0 and is similar to the PCC regret and lower than other algorithms. And on the right, we can see how there's an effective decrease on the difference between the actual density function and the surrogate function. And we also run experiments on real robots. These are run in the Robotarium at Georgia Tech. On the left, there's the look-ahead estimation coverage, and then the right, the Voronoi estimation coverage. And we can see on the top right, the actual density function. We see how initially there's an increase on the regrets given by the first purely exploration step, but as the robots move and take more samples, the surrogate is refined and the regrets goes to 0. I'm just gonna skip it and show you the final configuration and see how the regret progressively goes to 0. And even though we get slightly different spatial configurations, they correspond to similar costs. In summary, we presented an algorithm for simultaneous learning and coverage of initially unknown spatial fields with 2 different sampling strategies. One centralized, where the points are chosen sequentially, and another one where the robots are constrained to pick these points within their Voronoi cells. We offer provable guarantees on the asymptotic no regrets of the algorithm. And we shown improved performance both in simulation and on experiments on real robots. Thank you for your attention.
Can you hear? Okay. So thank you very much for the nice talk. I'm curious to see if you have any idea of how the method would perform with time varying density functions.
Yeah, thank you, Lorenzo. Nice to see you. Yeah, I haven't had an intuition and I haven't tried it with it, but I think it depends on the time scale that you have on this change of the density function. I think if you can have some time scale where you know that your features are varying with a certain like frequency or time scale, and you can take samples at a higher frequency. I know there's papers on estimation that deal with that, but I just haven't had a deeper look on the literature. But this is something that we've actually been thinking about, not because directly we're going to do the next step, the time varying, but just because we're working towards the decentralization, and what that happens, you need to have this knowledge of the different time scales. But thank you. Hopefully we'll know soon something.
Is there any other questions? If not, we thank the speaker again. Thank you.
Thank you.
Next talk would be GVGExp, communication constrained multi-robot exploration system based on generalized Voronoi graph. And the presenter will be Kizito Masaba, if I pronounce the name correctly. I apologize if not. Are you?
Yes, you did. Thank you. Can everyone see my screen now?
Yeah, we can see you.
Great. Hey everyone. Thanks for coming to my talk. My name is Kizito Masaba from Dartmouth College, and I'm going to talk to you about my work called GVGExp, a simple communication constraint Multirobot exploration system that is based on generalized Voronoi graphs. It was done in collaboration with my advisor, Dr. Alberto Quattrini. The current technological advancements in robotics have enabled exploration of remote regions, such as mapping shipwrecks underwater and mapping tunnels. And with the use of Multirobot systems, such missions can be greatly simplified as tasks are divided amongst the robots. The efficiency of a Multirobot system is dependent on how well the coordination is done amongst the robots through communication. However, these environments have various unfavorable communication constraints that may not enable such coordination. So our goal is to design a strategy for Multirobot exploration of unknown communication constrained environments, which minimizes the number of communication events and path interference. Several works have been proposed in the past that address different communication constraints, and many of them assume unlimited communication. We can categorize these works into two main categories: the continuous connectivity cases and the recurrent connectivity cases. For continuous connectivity, in these works, they usually assume they aim at maintaining a communication among the robots throughout the mission, with the goal of allowing them to communicate at any one moment throughout the mission. And in case they have a base station, they aim at maintaining a communication link that ensures that information is updated at the base station all the time. Much as it allows improved situational awareness amongst the robots and at the base station, it requires high bandwidth, which may not be favorable in some environments, and may also limit how fast the robots can explore the environment. In contrast, the recurrent connectivity cases do not maintain a continuous network, but they define predefined rendezvous locations where they can meet and share information. In case they have a base station, they regularly return to the base station to share data, and this allows them to maintain updated information at the base station. The common drawback with both of these approaches is that they share whenever there is a chance to share data. They just continuously share without, even when it's not necessary. So our goal is to implement a recurrent connectivity strategy that only allows sharing of data when it's needed, and we shall talk about more about what I mean by that, when it's needed. Our approach is based on the topological structure of the environment. We use information of the topological structure of the environment to obtain more information for guiding exploration and communication. So suppose we have two robots deployed to map such an environment. The robots are equipped with a range scanner and a Wi-Fi transceiver for communication. And the robots will move around the environment, collecting scans of the environment, and those scans will be integrated into an occupancy grid using a SLAM module. And based on this occupancy grid map that is obtained, we generate a generalized Voronoi diagram on top of it that encodes the semantic information of the environment. A generalized Voronoi diagram is simply an undirected graph that cuts through equidistant points in space, whereby 2 points which are equidistant in space form an edge on the graph, and more than 2 points form a midpoint on the graph. Any other node that has only one neighbor on the graph is called a leaf. So with this graph, we can capture the various semantic information of the environment, such as corridors and junctions. And this has been used in the past for exploration and obstacle avoidance, but you extract more information on top of it in order to guide communication and coordination. So how do we use the graph? We introduce a unique property called the gate. A gate is simply a node on the graph that is a route to a unique subtree of that graph. So if you have an initial graph such as this, You can identify nodes like the ones marked by the crosses, and these nodes extend into unknown regions which can be explored, and this we call them get regions. And using this property, we can decide on how we can do the deployment and decide on when to communicate and also explore. So let's start with deployment. A robot can be assigned to the nearest get to explore the get region. So if we have like two robots, the blue one and the orange one, we can deploy them sequentially so that each of the robot is exploring a unique region. So let's say the orange one is deployed to a lower gate, and then the blue one is deployed to the upper gate. We can see that the robots will continue to explore within unique get regions, such that they do not have to communicate or interfere with each other. But as they do, they visit leaves which are closest to the frontier, and they do that in a depth-first search until the whole get region is explored. But they can also coordinate in order to avoid path interference, and coordination is done through it's done every time they communicate. Now, when is communication necessary? Something we talked about earlier. We identified 3 scenarios in which communication is necessary. First, at deployment, like we've discussed, to avoid path interference, and also at a junction in order to avoid the robots going into other robots' regions, or when returning to an already explored region. The final one is when the robot has completed exploring its whole get region and is trying to find a new gateway to be exploring. This is also important because that way the robot will not be able to go to a region that is already explored by another robot. So basically, this is how the exploration works with this approach. And just to show you a quick demo, here we are comparing two approaches, our case, the GVGExp case, and the baseline where the robots continuously share data as long as they're within communication range in order to improve their situational awareness. And as we can see in the demo, the blue robot on our case and the green one, each is deployed at a unique get region, and they all start exploring. And as they go on, you'll notice that at a midpoint, or when they're trying to return to their or an already explored region, they'll establish a connection which is represented by the green line that is cutting through. And at those points, they'll communicate to check whether they are exploring unique get regions or not. If they are not, then that's when they can decide on how to harmonize, reconcile that conflict. And once the robot, like the blue robot, has completed its get region, it communicates and finds a new gateway it is going to explore. As you can see, we have almost completed the exploration, and we have only 12 established connections according to the graph, compared to the best case where they're always communicating and they already have 100 communication events. So this demonstrates how well our method is able to minimize the number of communication events. All right, for evaluation, we tested the robustness of our method in 3 different environments. One is an unstructured environment like a cave. Another one is a spacious environment like a city, and then a structured one like an office. And with that, we also compared the performance of our approach with 2 other methods: the baseline case, where robots are continuously sharing data, and the recurrent connectivity case, where the robots are homing, like they get back to the base station when they accumulate a certain amount of new information. So when we look at two scenarios. One is when a robot believes that the base station has at least 50% of new information, and when it believes that it has at least 90%. So in short, you can think of it as when the robot has accumulated 50% of the information from the environment, it should be able to go back and go back to the base station and share. Or when it has accumulated 10% of the information, should be able to go back and share. With that, we also do 5 simulated trials in each environment with 2, 4, and 6 robots, and we evaluate them based on communication and how they do exploration. Right, just to look at now, quickly look at the results of communication. Here we show on the bar plot, we show the number of established connections for each of the robot teams across all the environments and the methods. And we see that GVGExp has very low established connections compared to the baseline. And this can be attributed to the fact that the baseline is continuously sharing data. But in cases where there is low bandwidth, or like there's limited bandwidth in the environment, that is allowed in the environment, there will be this high number of established connections will be a great drawback to the mission. So this shows that GVGExp is performing pretty well compared to the baseline, and it actually performs comparably to the recurrent connectivity cases. We also notice that as the number of robots increase, as we increase the number of robots on the team, the baseline number of connections keeps increasing because the communication is dependent on proximity of the robots. But in contrast, the GVGExp method and the recurrent connectivity does not change as the number of robots increase, because our communication is not dependent on the proximity, but rather it's dependent on the nature of the environment. For exploration, we show how fast the robots explore 90% of the environment. And the GVGExp method is shown by the blue line, and we can see that it explores much faster than its counterparts. And this can be attributed to the introduced property of the gate that allows maximization of coverage initially during deployment and as the robots continue to explore. And this, because of that, the robots spread out well and they cover much more environment than its like the other methods. In summary, we've introduced a novel multirobot exploration communications and a communication strategy which we call the GVGExp. It is based on a unique property we introduced called the gate that guides communication and coordination, and our simulation results validate the effectiveness of this approach. In the future, we aim at designing a criterion for determining the number of robots that can be assigned to a given region, because we notice that some gate regions may be much wider, so one robot may not be enough. So we need to decide on how we can deploy more than one robot in one gate region. And we also want to assess the impact of uncertainty to the generation of the GVGExp that guides the exploration. And we also hope to explore different potential path interference cases. Like for instance, when two robots meet up in the same gate because they have failed to communicate, that's a scenario we need to address. And finally, we want to test our method on the actual robots. So this wraps up my talk, and I'm grateful for your audience, and I'm happy to take some questions.
Thank you. Thank you, Kizito, for an interesting talk.
Thank you.
There is no question online. Is there any question in the audience? So the question I had, you kind of mentioned in your future work, but I would ask anyway. So is there any formal guarantee for collision avoidance of, if you have, for example, multiple robot, imagine in the underground mine, would be really important, and imagine those robots usually are huge and have non-holonic constraints, and it have non-trivial movement. Is there any formal guarantee that you can avoid the collision between the robots in your exploration?
Yes, usually the robots have a local planner that helps in obstacle avoidance, both static and dynamic obstacles. But you see, this comes with a cost. Like when the robot is looking for an alternative path in case of a dynamic obstacle, it is going to be costly. And so in order to avoid all that, we try to add this extra precautionary measure to avoid any kind of potential interference. But in case that happens, those robots usually have a local planner that can guide them in avoiding obstacles. And in case they are too big, then you want to ensure that the environment they're exploring in is safe. Otherwise, even the environment would lead to collisions in its own. So, yeah. I think this is just an extra advantage we add to the local plan that is already on the navigation plan.
Thank you. Let's thank the speaker again. The next paper is Local Advantage Actor-Critic for Robust Multi-Agent Deep Reinforcement Learning. And this is a paper actually as a finalist for Best Paper Award as well. And the speaker would be Yuchen Xiao. I'm sorry if I pronounce your name wrongly.
Hi, everyone. This is Yuchen, a PhD candidate from Northeastern University. It's my great pleasure to share our work on this symposium virtually in such beautiful campus of University of Cambridge. Today, I'm going to present Local Advantage Actor-Critic for Robust Multi-Agent Deep Reinforcement Learning, a joint work with my lab mate Xueguang Liu and my advisor Christopher Amado. Let's start with the standard multi-agent RL framework and partial observability, where there are multiple agents interacting with the world by taking actions in a state based on their observation action histories. As a result, the world transits to a new state according to the underlying dynamics and issues a reward to the agents. Agents continue doing this and use this information to update their policies in order to maximize the return. Typically, we focus on fully cooperative case that has only a global reward function. One obvious solution method is to perform centralized learning and control, treating all agents as a big one. However, this requires fast and perfect communication over agents in both offline learning and online execution that is often difficult to be guaranteed in many real-world settings. Or we can have fully decentralized learning and control. It doesn't have strict requirement on communication, but due to the lack of information sharing, it often cannot learn rich corporations. Essentially, from each agent perspective, the world now becomes non-stationary as other agents learning and changing at the same time. To improve the learning of decentralized policy, recently centralized training for decentralized execution paradigm becomes the most popular choice in multi-agent RL community. Where during the training, agents are allowed to access to other agent information or even the ground truth state to optimize decentralized policies. But in execution phase, agents behave purely based on local information. By leveraging centralized info, this framework is promising to promote cooperation and overcome environmental non-stationarity. Well, remember that agents all use the same reward signal. So this learning framework encounters a credit assignment problem. Agents have to reason about each own contribution to the global reward. How to best exploit CTDE as well as solving credit assignment remains open. In our work, we contribute to this by proposing a new robust local advantage actor-critic algorithm, ROLA. ROLA learns a separate critic for each agent using the centralized critic, but in a novel centralized training for decentralized execution way. By using this local critic, ROLA is able to provide low variance estimation on the decentralized policy gradients, as well as achieving credit assignment implicitly. Finally, we show ROLA can outperform other baselines in a variety of benchmark problems. Our work focuses on learning decentralized policy via policy gradients. The simplest method is independent actor critic, where each agent independently learns its own action value function as the critic and update its policy, a mapping from local history to action space via this policy gradient. In order to achieve variance reduction, a common choice is to learn history value function and as the critic, and then use it as a baseline, which ends up with this advantage action value estimation and use it for computing the policy gradient. As we mentioned in previous slides, this method suffers from environmental non-stationarity and the lack of information sharing. In order to learn better decentralized policy, independent actors with a centralized critic is proposed. The essential idea is to learn a joint action value function as a critic, as well as accessing global information during training. This centralized critic is then used for computing each agent's decentralized policy gradients to facilitate the update of decentralized policies in the direction that optimizes the global collaborative performance. While in the online execution, agent can just throw away the centralized critic and run their own decentralized policy. Coma is one of the pioneers proposing such idea and also takes one step further to reduce learning variance and achieve credit assignment by having this counterfactual advantage value estimation, which is calculated by using this centralized critic to minus a marginalized value over the particular agent S policy. Such idea is very beautiful. However, we detect that Coma naturally cannot achieve high efficiency on variance reduction, which will also potentially lead to less effective credit assignment. This can be visualized by further deriving Coma's policy gradient by expanding the joint policy here into the policy of agent I and other agent joint policy. We can rewrite this expectation like this, and then we move the log part out of the second expectation because the pi here is not associated with other agent joint policy. And finally, we reached here. Now this is exactly telling us this expected advantage value over other agent possible choice is what we do want. However, Coma only use a sampled value under a specific other agent joint action in the policy creating computation. It does well cause high variance. The higher variance on this advantage value estimation, the worse credit assignment will be because the computation here is basically trying to measure the contribution of agents I's action to the joint queue here. To improve this, we really need to have the decentralized policy gradient with an expected advantage value, which actually can be done by two simple solutions. One is to explicitly calculate this expectation using the learned central queue. We call this way as ECA, and I will further discuss why it cannot work well in the results session. The other way is exactly what ACE2C trying to do. However, it naturally has the two fatal issues as I mentioned earlier. Motivated by this, we propose ROLA that approximate a local expected advantage action value for each agent in a novel centralized training for decentralized execution way. ROLA first learns a centralized critic conditioning on global information and joint actions by minimizing this on-policy error. Same to other method, by having this kind of centralized critic, we can leverage centralized information and help to promote the collaborative behaviors when updating each decentralized policy. At the second stage, we learn a local critic for each agent by minimizing a special TD error here, where the target action is extracted from a joint action that's sampled using the learned centralized queue in the first step. This particular sampling operation generates actual joint action selection data for training rather than only depending on the data from decentralized execution in other CTD-based methods. It also implies that starting from next step, agents will all behave in the centralized way, which actually enable this local critics learning considering other agent future action selections in order to alleviate the impaction of the environmental solutionality. Meanwhile, by having two value function approximator in the updating, we can counteract the overestimation often existing in the learning with single function approximator. In the end, we can use this local critic to compute the expected advantage value for each agent to achieve low variance on its policy gradient estimation, as well as implicitly finish credit assignment because the value here is only with respect to agent I's action. Our empirical evaluation considers a variety of benchmark problems with partial observability. The properties of these domains differ from each other in terms of reward density, environmental stochasticity, collaborative format, and the number of agents. We evaluate the ROLA against a wide set of state-of-the-art multi-agent actor-critic methods, and they achieve variance reduction and credit assignment in different ways. Some of them are on-policy learning, some of them are off-policy learning, and three of them relying on the value factorization network to decompose the centralized critic into individual critic. And the underlying architecture being used there is similar to what Professor Weston just mentioned in his keynote talk. We first compare ROLA with these methods that are not depending on value decomposition network. We plot the mean testing return with 95% confidence interval over 20 independent training trails. We change the difficulty in each task by either increasing the grid word size or decreasing the observation range. Overall, our method ROLA, the red line, outperform other baselines by converging to a higher value with less performance variance, or having better sampling efficiency to reach the optimal performance represented by the dashed dot line in this box pushing domain. In the less curved task here, ROLA achieves almost same performance as IA2C and the central V, but slightly faster. Next, we compare ROLA with this value decomposition network-based method. Given a domain, the ground truth relationship between the local Q values and the joint Q is often unknown. While each baseline method considered here impose a particular constraint on the decomposition of the joint Q. We suspect this is why these baselines could work well in certain domains like the capture target, but in other certain domains, they are not that competitive with ROLA, as the fact that ROLA doesn't have such constraints on learning either the joint Q or the local Q. In the end, we see that ECA performs much worse than ROLA. This is mainly because explicitly calculating the ECA value using the learned centralized Q value function leads to a strong single proximity bias when the centralized critic has not been fully trained for all agents' joint actions. More detailed discussion can be found in our paper. In conclusion, in this work, we propose ROLA, a new multi-agent actor-critic method that adapts CTDE paradigm in a novel way to learn each local critic using a centralized critic. ROLA learns decentralized policy using the data generated from both joint perspective and the decentralized execution. By using the learned local critic to compute the decentralized policy gradients, ROLA achieves better variance reduction and credit assignment, such that performing faster learning, higher return, and lower variance than other state-of-the-art multi-agent actor-critic methods. All right, that's all. Thank you for your listening. I'm happy to answer any questions.
Thank you.
Thank you.
So there's no question online. Is there any question here?
Hello. I just had a question about your diagnosis of the problem with coma. So if I understand correctly, you were saying the counterfactual baseline has high variance because it depends on a sampled set of actions for the teammates.
Yeah.
Which, I mean, that makes sense to me, but it's like the purpose of the counterfactual baseline is not to have low variance, but to co-vary with the value function whose variance it's trying to reduce. And that value function conditions on exactly that sampled joint action. So it seems like marginalizing with respect to those joint actions would actually reduce the effectiveness of the baseline by making it co-vary less with the value function.
Okay, let me back to this slides. So when I say the counterfactual value function in original coma has high variance, because I'm from the perspective from the local agents, since this action is actually exactly what we hope to have. Well, you can see that in coma, when you calculate the policy gradient for a particular agent I, we certainly fix the other agent's joint action there, but we do want is the expected value over other agent choice. And here, yes, in coma's counterfactual advantage value computation here, we marginalize the particular agent I's policy, but you can imagine this certainly will reduce the variance if the variance caused by agent I. But if the variance caused by other agents, I do think this baseline will not work that well to deal with that variance, because we fix other agents joint action here. Did I answer your question, Shimon?
I can't see the equations anymore, but I think I understand. But then the policy gradient in that case doesn't depend on Q, it depends on V. It's a gradient based on the TD error. So it doesn't, the term whose variance you're trying to reduce already doesn't condition on the joint action. Is that right?
I think the policy gradient is still depending on the Q, right? Because we are estimating the advantage value of the advantage action value, and the advantage action value depending on the Q.
The advantage can be estimated with the TD error using a.
Oh yes.
But I can't see the equations anymore, so maybe it's better if we talk about it offline.
Okay. Thank you for the question, Shimon. Nice to meet you.
One question from anonymous attendee, and I appreciate if you answer really brief. Could you please comment on what was typically the size of the benchmark problem that you used, how or why partial observation is expected in such application, especially if few relatively closed space robots are involved, and if ROLA is scalable to larger multi-robot system?
Okay, that's a very good question. I don't know if it's, maybe you still cannot see the slide of the environment, but in the benchmark problem that we considered, so I think the biggest size in terms of the number agent is 4, and the set of the joint actions reach like 4,000. Yeah, the joint space, and then I admit that ROLA certainly has a limitation for scale up to larger problem, because we need a centralized queue to sample the actions. But in terms of this, I think we can solve this in the way such that we can combining like the value factorization network with ROLA. For example, you can factorize the big joint queue. If you think the big joint queue is hard to learn because the curse of dimensionality, we can factorize into small set of joint queue, and then we can think about how to manipulate those subset joint queue to better learn the local queue for each agent. And the other potential way to adapt ROLA to larger problem is actually the other work that I'm trying to do. Like we introduce macro actions into multi-agent case, especially for real-world robot problems. You can give the abstractions of the over the action space and the state space, and in the high-level abstraction level, certainly I think ROLA is missing to be implemented there. And yeah, we can further check how ROLA performance and also think about how to improve the ROLA.
Thank you, Yuchen. Thanks to speaker again. And
thank you, everyone.
On to the next talk. The next talk would be the parameter identification for multi-robot system using optimization-based controller. And the speaker is Jaskaran Singh.
Yes.
Are you with us?
Yes, I am ready. Just give me 1 second, please. All right, so does everybody see the full screen?
Yeah.
Excellent, cool. All right, well, good afternoon, everybody. It's nice to see you. My name is Jaskaran. I'm a PhD student in CMU. I will be talking about parameter identification of multi-robot systems that use optimization-based controllers. So the goal of this work is to reverse engineer the tasks being performed by individual robots in a team by monitoring their individual positions and velocities over time. So this is the outline of this talk. I'm just going to begin with the motivation and go through real fast. To begin with, I would just say that multi-robot systems are very useful for many tasks, and therefore they're worthwhile to study. I mean, that's why we're here. Synthesizing safe controls for various tasks is a forward problem, and I would say that it is relatively well studied. So when I say forward, it's like the synthesis problem. On the other hand, the inverse problem, that is task inference in the face of safety constraints, has not been explored that much. Now, observer-based inference has several applications. For example, our observer could be another robot team. And here the question becomes, how can this team imitate an expert team by just watching it? Or the observer could be an adversarial robot team, in which case the question becomes, how can the observer easily sort of reverse engineer the task that is being performed by the good team that it is watching? And what can we do to prevent it? So the research that we did in this paper is an attempt to answer those questions. So in this work, we derive estimator agnostic identifiability conditions based on persistency of excitation, under which the observer's estimate of the task parameters will converge to the true parameters. We conducted simulations, and we used UKF and a recursive least square type estimator to show that the inference of parameters succeeds when these conditions are satisfied, and the inference fails when these conditions are violated. And our results also extend to batch inference algorithms that are based on inverse optimization. All right, so with that, let us look at the forward problem, that is task completion with safety constraints. So suppose we have n robots in the system. I am just going to focus on one robot, that is robot I. This can be applied to the other robots as well. Now, the job of this robot is to find a control UI to make it complete a task parameterized by theta I while avoiding collisions with every other robot in the team. Now, let's just assume that there is a nominal task-based control that is U cap theta I that depends explicitly on the task parameter theta I, and take it as a given that this control guarantees completion of the task. For ensuring safety, a linear constraint has been proposed on the control that guarantees a safety margin of d sub s between every pair of robots. Now, to mediate between the task satisfaction and safety constraints, a quadratic program has been proposed in prior work that computes a control that is closest to the task-based control and also ensures safety by posing them as inequality constraints in this optimization. So the robots use this control synthesis module to figure out their velocities because they're sort of single integrator dynamics robots. So going forward, this is our assumption of the control synthesis. Now let's come to the main topic of the paper, that is inference of the task. So the inverse problem requires us to develop an online algorithm to learn the task parameter theta I for all the robots in the system by tracking their positions and velocities, the velocities being computed by the optimization that we just saw. So as an example, suppose there are 4 robots. Each of them is trying to go to a certain goal location. Then the task inference problem, for example, can be to figure out what that goal location is by watching the positions and velocities over some time. Obviously, we're not going to wait for the robot to reach the goal. We just want to infer before the robot has reached the goal where it is trying to go. Well, why is this inference difficult? Well, the reason this problem is non-trivial is because the robot dynamics depend implicitly on the task parameter through this optimization. So theta I shows up in the cost and in this constraints as well. And so through that filter, theta I ends up influencing the dynamics. But most estimators require an explicit analytical relation between the dynamics and the parameters, and that we don't have. So to fix that, let's see how we can do that by using the KKT conditions of this control synthesis optimization that we just saw. Recall that this is the robot's problem, which is this quadratic program. We will use the KKT conditions of this problem to derive an explicit relation between theta I and UI star. And we'll do that by converting this to an equality constraint problem. This problem is inequality constraint. We'll see how to convert it to an equality constraint one. So what are KKT conditions? Well, they're just like necessary and sufficient conditions that are satisfied by the optimizer UI star. We have stationarity, which is just setting the gradient of Lagrangian to 0. We have primal feasibility, which is just the feasibility of the constraints of the QP. And then we have dual feasibility, Lagrange multipliers and R-negative and complementary slackness. Oops. All right. So using these conditions, we can define two sets of indices. These are known as active and inactive constraints. The set of active constraints is the set of all those other robots for which the constraint is active. That means that the ego robot, intuitively, this means that the ego robot worries about collision with the active robots. Inactive constraints are those for which the optimal control UI star sort of satisfies a strict inequality. So there's a strict inequality in the inactive indices. Now, an observer can easily figure out which constraints are active by just measuring the positions and velocities of the robot. That is easy. So given these sets, the observer can pose an equality constraint problem as follows, where you have equality constraints here with respect to the active constraints only. So now we have two problems. The first one is the problem that the robot is trying to solve, which has inequality constraints with respect to every other robot in the system. Then we have the observer's guess of the robot's problem, which has equality constraints with respect to the active set only. By way of our construction, both of these problems give the same answer UI star. And it is the second problem that we'll use to derive the explicit relation between theta I and UI star. So how do we do that? Given this equality constraint problem, we can look at three cases. Actually, the paper talks about 6 cases, but I'll just use these 3 to convey the idea. These 3 cases correspond to when there's 0 active constraint, 1 active constraint, or 2 active constraints. You go till 2 because there are 2 degrees of freedom in the control. So the first case, as I said, is when there is no active constraint. This means that there is no other robot that the ego robot has to worry about for collision. So your optimization is just to minimize difference from U theta. In this case, the optimal control becomes U cap theta itself, which is C times theta plus D. And so the dynamics of the robot is C times theta plus D. And so theta is influencing the dynamics. So it's completely determined, the robot motion is completely determined by dynamics. So parameter inference will be possible in this case because theta is featuring in the dynamics. On the extreme end, we have the case when there are 2 active constraints. This happens, in this case, the control UI star is completely determined by the safety constraints itself. This happens when there is so many robots that the robot's control is sort of inundated or by ensuring safety. And so it forgets about doing the task and just worries about safety. And so what ends up happening is that the robot's control does not depend on theta. Persistency of excitation gets violated. And so therefore, in this case, parameter inference of theta will fail. So let me show you some simulations to convey the idea. So in this video, you have this robot that is trying to go to this goal location. There are static obstacles around the robot. Because all these obstacles are far away, we're trying to infer the goal location using an adaptive observer type estimator and a UKF. And as the robot is trying to go to the goal, both of these estimators are able to figure out the goal because there is no obstacle that is active. But here, as the robot is trying to move towards the goal, first obstacle 1 and 2 is active and the estimators don't move. They don't know where the goal is. And obstacle 3 and 4 is active and the robots, here, let me just go back. They still don't know where the goal is. But as soon as the robot exits the active zone, the estimators are able to figure out where the goal location of the robot is. So after exiting the active zone, estimation is successful. This is what we expected from our theory as well. Here's the same thing for multi-robot systems. So both the estimators, the adaptive observer and unscented Kalman filter are able to figure out the goal of the ego robot because there are sometimes, so the ego robot is the one in the red, and this is because there are sometimes that this robot has less than 2 active interactions. If there's 1 active interaction, parameter inference will succeed. And so because there was less than 2, all the estimators errors converge to 0. So let's wrap up. In this paper, we developed identifiability conditions under which the convergence of the observer's estimate of the robot's task parameters to the true parameters is guaranteed. And our results are agnostic to the choice of estimator. In this paper, we used UKF and RLS type adaptive observer, but these conditions are independent of what choice of estimator you use. And we've tested that in a different paper with respect to inverse optimization algorithms. And so with that, I'd like to thank you for listening to my presentation, and I'm happy to take any questions.
Thank you, Jaskaran. There's no question online.
Hi, thank you for the interesting talk. A quick question. Is there a relationship, or I don't know if you know that terminology from the control side, is there a relation between what you had been doing there and something like explicit model predictive control or multiparametric programming, quadratic programming, multiparametric one? Because there some, I don't know, 15 to 20 years ago, there was a lot of research on that, where also the feedback then was piecewise fine with respect to that parameter, like it was in your case. But my question on that basis, there it is well known that that it explodes rapidly with the dimensionality, especially with regard to the constraints, and your constraints scale with your whole input vector U. So in control, that's why explicit MPC, it's only for small systems. So in that regard, would that be an issue? I mean, in that scenario that you looked at by hand at specific cases. I mean, these algorithms, they do that algorithmically, but even they explode because the different active sets that can exist, the number of them increases combinatorically, so exponentially with the dimensionality. Is that a problem for your scheme as you consider more robots, or?
Yeah, so that's a good point. I learned about the multi-parametric programming after I'd submitted this paper, and I noticed the connections between the two, so here we don't have explosion because our control synthesis optimization is in the size of the problem is in the number of degrees of freedom of the control. So if I had quad rotors instead of planar robots, then the number of cases that I would have had to consider would have been really large. But here there were 6 cases, so I could tabulate all of them, and that's all there in the paper. As far as active set is concerned, we can just immediately know what the active set is. We don't have to see all possible combinations of the active sets. That is exponential in the number of robots. You're right about that. But we could avoid that problem by just watching the robot, seeing what its control is, and evaluating this activeness condition. And that's how we knew what the active set of robots is.
Oh, that is nice. And so it scales with the dimensionality of the input of an individual robot, not with the combined group. Ah, that's interesting. Thank you.
Yes.
Thank you, Jaskaran. Let's thank the speaker again and move on to the next talk. The next talk would be robust perimeter defense using control barrier functions. And the speaker is Carlos Nietegronda. Are you with us, Carlos? Oh, it's Luis.
Hello, can you hear me and see my presentation and only my presentation?
Yeah, we can see you and your presentation, and we can hear you well. Hi, Luis.
Perfect. Hi. So thank you everyone for being here. I will present the paper Robust Perimeter Defense using Control Barrier Functions. So let's get to it. So let me tell you about the formulation of the perimeter defense problem that we have. So we have a known perimeter in the plane with straight line segments as its sides. We have an intruder who wants to cross the perimeter undetected. So we assume that the position of the intruder can be measured. We assume that its velocity is continuous and bounded, and that its maximum speed is known. Let me be clear here. We do not need a function of time describing the position or the velocity. We only require the measurement of the position, so a sensor that is measuring the position of the intruder and the bound on its speed. That's all we need. To defend the perimeter, we're going to place robots on the line segments that make the perimeter. And these robots are not point robots. We're considering robots that have a body and that we know the size of the body in the direction of the line segment. We assume that these robots move on the line segment, so that's where they live. We assume that they have first order dynamics, and we also consider that they have a maximum speed. We allow the intruder to be faster than the defender. And this is something that other versions of pursuit and evasion games do not allow, but we have no problem with that. So the intruder can be faster than the defender in our formulation. And so what we want is to determine the control action for the defender such that the body of the defender overlaps with the intruder whenever the intruder tries to cross the perimeter. So this way the defender stops or catches the intruder when he tries to cross the perimeter. And well, the red square shows the mathematical formulation of what I just said. So to ensure this, that this overlap happens when the intruder tries to cross the perimeter, we calculate these functions HL and HR, L and R for left and right, although of course in the plane the orientation of the line can be, well, anything, but just for the visualization in this example is left and right, L and R. Anyways, we compute these functions that are related to the difference between the time it takes for the intruder to reach the endpoints of the line segment that the robot is defending, and the time it takes for the defender to reach the same endpoint. So the idea is, of course, that if the intruder takes longer or the same amount of time to arrive than the defender, then the defender can always arrive on time to the endpoint. And so the intruder will not cross the endpoint unchecked because the defender will be there. And so looking at only the endpoints, we can prove that if we manage to somehow ensure that these H functions, that is the difference of these times, is always greater or equal than 0 for all times, then we can guarantee that we can defend not only the endpoints of the line, but the whole line segment. And so then the problem is about, well, how do we ensure that these functions H are always greater or equal than 0 for all times? And we do this using this control theory tool called control variable functions that was mentioned in the previous talk. And so using this control theory tool, we compute the controller for the defenders such that we can ensure that these functions H will always be greater or equal than 0. And therefore, we can ensure the defense of the line segment. The details of these are, of course, in our paper. So what am I talking about? Well, the simulation of this looks as follows. So on the left, you can see the robots on the perimeter and the intruder that is crossing the perimeter. And the idea is that every time the intruder tries to cross the perimeter, so goes across the perimeter, there is a defender there to catch it or to yeah, it just makes sure that that someone detects the intruder as it crosses the perimeter. And of course, as it is common in simulation, everything works fine. And as you can see in the right, we have the graphs of the H functions, and they are always greater or equal than 0, and therefore we can guarantee the defense. So that's great. But there's a little bit of an issue here. So the idea is that we have these functions H greater or equal than 0. And that's fine, but then that means that we are allowing these functions to be 0. So we're allowing the time that it takes for the intruder to be the same time that it takes for the defender. That is, we are allowing the defender to arrive just in time to the encounter. And in simulation, that's great, but in real life, any perturbation that causes a delay in the defender, such as a bump on the road, a gust of wind, or delays in the actuators of the defenders, may cause the defenders to be late. And then the defense can fail. So that's an issue. And we have experiments with our algorithm, and they look fine. They look just like the simulation. But we know that these experiments were on in the Robotarium, and we know that the robots in the Robotarium have a little bit of a delay of around 200 milliseconds. So even though it looks fine, and if we check, yeah, the defense is never broken, once we graph the values of the H functions from the data from the experiment, we can see that these functions indeed go below 0. So what's happening here? What's happening is that even though the defense is not broken, we lose the guarantee of a successful defense. Remember that having the H functions greater or equal than 0 is a sufficient condition for defense. So what we're losing here, with them being less than 0, is the guarantees. And well, having no guarantees is not good. We like to have guarantees because we're doing controls. So what we did in this paper that we're presenting at MRS is we robustified our algorithms or control laws for perimeter defense against time delays. And so how did we do that? Well, the way we did it was we included an extra parameter in our equation. So this is the equation that we use to model the time the intruder takes to get to the endpoints of the line. And we included an extra parameter, that delta parameter over there. We included a parameter, and that changes the equations, and everything changes. So our paper is basically the proofs of why making this modification works and why it provides the robustness. So the proofs are all on the paper. I invite you to take a look at it. But let me give you the intuition behind it. So roughly speaking, this term makes the intruder look as if it were closer to the endpoints by a distance delta. Or if you want to think about it in terms of time, it makes the intruder look as if it is at a time, as if it is delta over the maximum speed of the intruder ahead of time. And this is what makes, what forces the defender to arrive early to the encounter. So this is the mechanism that provides the robustness. And so we made these modifications in our control laws. We have all the proofs that everything works. And then we implemented it in the Robotarium again. And so the experiment looks pretty much like the other experiment. Again, if we look at it, every time the intruder crosses the perimeter, there is a defender there to meet it. But then when we take a look at the H functions, we see the difference. And in this case, we see that indeed all the functions are now greater or equal than 0, and we can see the effect of this robustness that we have now against time delays. And so that is how we got a robust perimeter defense using control barrier functions. And I'll be happy to take your questions now.
Thank you, Luis. Is there any questions from the audience? Yes, there is one.
All right, thanks for the talk. I didn't quite understood whether this approach always works when the adversary agent is becoming faster and faster. So I see it can be bounded, but let's say if it's 20 times faster than the defending agent, then surely you should need more defending agents to some extent, right? If you had just a single defending agent, why could it? You cannot construct a continuous curve that brings kind of the agent over the line without being protected. In your example, there was quite a lot of inertia of the agent that was attacking. Can you comment on this?
Yes, indeed. So let me share again. And yeah, so if we look at here, yes, we have, for example, this line segment at the bottom. There's only one robot defending it. But we have this line segment at the top. There's 3 robots defending it. So it's really, we broke this line segment into 3 line segments, and then each robot has its line segment. Yes, so I'm gonna stop sharing now. So what you're talking about, we discussed it in depth in our previous paper where we discussed this perimeter defense strategy. And indeed, so the way it works is the following. If you give us, for example, the speed of the intruder and the sizes and the speeds and the number of robots, of defender robots, we can tell you based on that, the lengths of the line segments that you can defend. On the other hand, if you give us the speed of the intruder and the perimeter that you need to defend, we can tell you how many robots and of what sizes and of what speeds you need to have to defend. And this solution is not unique because if you have larger robots, then they don't need to be as fast. If you have smaller robots, then they need to be faster. So for example, in the example that we saw, there was one robot defending one large line segment, and that's because it was a fast and big robot.
Can I just have a follow-up question? Do you know only the position and velocity of the agent at the time, or also in the future? So you know the full trajectory of the attacking agent?
No, that's what I mentioned at the beginning. We do not know. We do not need to know the trajectory of the intruder. We only need to know its position. So a sensor that tells its current position and the bound on its speed. But we do not need to know the trajectory, so no function of time, and we do not need to predict its motion. This is a completely reactive control. So we only need to have the sensor that is telling us, at this moment it's there, at this moment it's there, and so on, and the bound on its speed. That's all we need. And that's one of the things that makes this defense strategy attractive, because we don't need to have all that information, and we don't need to make any prediction. It's a completely reactive controller, and we only need current position and bound on speed. That's all we need.
So there's 2 more questions. One online, Maria asked, how do you envision defending this perimeter using control barrier function, but without the robot being constrained to move in the line?
So yes, we have a version of this that we call it area defense. And so we have a similar problem, but instead of just defending a line that is making sure that the robot intercepts the intruder as it crosses the line, we have a robot that intercepts the intruder in an area. So it is there when the intruder crosses into, imagine a square. It is there to meet the intruder as it gets into the square, and then as the intruder moves inside the square, the defender is always there below it. So it doesn't go unchecked within the square. So yes, we have a version of this that is area defense, and we have a paper. It was published in the last IROS. So yes, there is an area version of this.
Thank you. Do you want to? It is very brief, and I appreciate Luis will be brief in answer.
We can do it offline.
Okay. So thank you, Luis, and let's thank the speaker again.
Thank you.
The last talk of this session will be design and simulation of a multi-robot architecture for large-scale construction project. Speaker is Vivek Thangavelu. Are you with us, Vivek? Can you hear me?
Hi, I can hear you. Can you hear me? And can you see my screen?
Yes, we can see you and we can hear you very well. You're good.
All right. Thank you. Hi, everybody. I'm Vivek Thangavelu from Cornell University, and I'm here to present on our work, design and simulation of a multi-robot architecture for large-scale construction projects. Advancements in construction automation holds promises to solve critical societal problems, allowing for safe, sustainable, and inexpensive construction processes. They also enable new classes of applications, such as extraterrestrial construction. With multiple space agencies revealing plans to establish human settlements in Mars and the Moon by 2050, 2050, it is imperative that we push for advances in construction automation. This would entail large-scale construction tasks, such as providing access to the site, leveling terrain, or building protective barriers, each requiring long-term autonomy in modifying and operating in unstructured environments. Since mobility is believed to be one of the basic functions of robots, our work focuses on ground robots that can modify unstructured environments through depositions in order to provide mobility for themselves and for other agents. Constructing navigable structures provides two capabilities. One, robots can move to new unexplored locations. Two, they can build structures many times the size of an individual agent if the intermediary structures are also navigable. We make use of a mathematical model in our prior work. Given a height function of the environment, Mars, or the minimal additive ramp structure, calculates the minimum additive deposition required to make the entire terrain navigable using locally sensed data. The animation depicts a robot building with different types of materials using local views in a 2D setting. The thick gray line depicts the height function, and Mars is depicted as the green line. If a robot makes the necessary depositions as shown in the shaded gray region, then it can make the entire terrain navigable. In our prior work, we used the model for constructing navigable structures in physical systems using different building materials. However, they were all limited to smaller settings, both in the scale of the environment and size of robot teams used. The focus of our current work is to showcase different large-scale construction scenarios using a formalized architecture in a simulation environment. More specifically, in this work, we propose a flexible system architecture, Marcella, that allows for a team of mobile robots to construct motion support structures in large unstructured environments using local interactions. The proposed architecture provides a means for formulating a construction project as a motion support structure construction problem and leverage the intrinsic decentralization of it. We demonstrate two construction scenarios in a modular simulation framework developed for the design and evaluation of coordination algorithms using our proposed architecture. Marcella is based on the well-known three-layer architecture that integrates deliberative and reactive approaches for controlling mobile autonomous agents. It allows for a decentralized multi-agent system to consist of heterogeneous agents, where each agent is deliberated to build a motion support structure to reach a known target location. Our contribution focuses on the various modules in the deliberative layer, which generate high-level goals to fulfill construction and coordination tasks. The building agent is tasked to build a navigable path to a target location, and the modules in this layer synthesize a tractable solution that is inherently coordinated to the environment state and local interactions. In this work, we depict multi-robot scenarios in a simulation environment, where the executive, reactive, and hardware layers are abstracted so that we can focus on the intrinsic decentralized coordination provided by the deliberative layer. More specifically, in our simulation experiments, each robot is modeled as a self-contained mobile manipulator. We've abstracted certain components of the robot system, particularly the low-level motion planners for movement and deposition. We generalize the deposition mechanism by allowing a robot to deposit small rigid blocks of a predetermined size. Essentially, in each deliberative step, the deliberative layer operates on a discretized height map of the agent's local environment and outputs the target deposition volume. Thus, the building agent builds a navigable path from the global origin to the global target location in a reactive manner based on the target location and the local environment state. Furthermore, by synthesizing target locations and construction parameters based on the agent's state, we can translate a construction project into a series of motion support structures. We'll look at a simple case scenario later on. Now let's take a look at how the deliberative layer provides a deposition target volume. The computational complexity of Mars and navigability is cubic in the size of the map. In order to keep the problem tractable, the global map is partitioned into smaller augmented local maps. The local map synthesis provides consistency for the local planner in the global deposition bounds, target location, and return path. This allows for decentralized coordination between robots as the actions taken locally are consistent across robots since they depend only on the target location and local environment state. To synthesize the augmented local map, the height function of the robot's local environment is first classified into navigable, occupiable, and reachable regions by the various modules in the deliberative layer. The local origin and goal are identified based on the robot trajectory and global target location. Now, putting all of this together, along with the Mars gap map, we have the augmented local map. This augmented local map is used by the navigable path planner to compose a plan to build a navigable path from the local origin to the local goal. Here, the cells with the blue font showcase the path being built by the planner, which is designed as an informed graph search algorithm with a cost function consisting of 3 terms. The first term is the total movement cost from the start node to a node n. The last term is a heuristic estimate of the cheapest cost from node n to the goal node. The middle term is the construction cost from the start node to node n. The construction cost of a node is a deposition required to make that node occupiable. The cells that will influence the occupiability of node n are first identified, and the Mars gap of these cells are summed together to determine the construction cost for that node. This way, we find a navigable path from the local origin to the local goal shown in the blue font. Finally, the target deposition volume for this path is derived from the chosen navigable path and the reachability map. The animation here showcases a single robot tasked to reach the top platform by constructing a motion support structure to it. The center of mass of the robot is depicted as a large green sphere, and the deposited material in each deliberative step has a specific color. The robot moves back and forth as the navigable region grows and shrinks with depositions up until the target location is also navigable. To showcase some of the benefits of the proposed architecture, we describe 2 large-scale multi-robot scenarios. The first one, a large mobile payload system with conservative motion parameters, is to be transported to an inaccessible target location in a large unstructured environment. A team of agile builder robots capable of depositing material in their environment are deployed to build a navigable path to the target location for this mobile payload. In the images here, the robots are spawned at the base station, shown in red, and are aware of the target location, shown in green. Each builder robot deposits material of a different color, as shown in the enlarged views, and the path is highlighted in yellow in the bottom view. Each robot has a limited material reserve and periodically returns to the base station for replenishment. The width of the path built is such that it accommodates the larger payload system to be transported and also supports 2 lanes of motion for the builder robots. Each robot runs a simple state machine to form a construction pipeline, where the robots maintain a minimum distance between them. Only the robot at the front of the pipeline is allowed to make depositions, and when it runs out of material, it returns to the base station for replenishment, and the next robot in the forward lane becomes the active robot. As such, a construction pipeline across many robots is maintained merely through local interactions in Marsala, since the depositions depend only on the environment state and target location. The robots were deployed in a topographical model of a portion of Valles Marineris on the planet Mars. We ran the tests for robot teams of different sizes and measured the number of simulation steps required to reach the final target location. The completion time reduces exponentially with the number of robots. However, it saturates at a team size of 9. The saturation is primarily due to the physical limitation of the simple construction pipeline approach. Nonetheless, this scenario showcases an approach to cooperatively build a navigable path in a decentralized manner using a simple local communication rule in a static target location. In the second scenario, a team of robots is tasked to level an uneven terrain as part of a site preparation project. The goal synthesizer module in the deliberative layer compiles goals based on the location of the robot and instructs them to use a small construction slope parameter throughout the mission. The robots were deployed at the larger flat area on one end of the terrain, and the simulation was run with lab and robots so that they can cover the entire area, where each robot deposits material of a different color. Each robot is initialized with the goal vector map shown here. The pointed end of the red arrow represents the target location for a robot located at its rear end. When a robot is deployed, it first finds the closest rear end of the available goal vectors and positions itself to it. It then begins planning a flat construction path because of the small slope parameter to the target location given by the pointed end of the arrow. As such, the robots begin to build flat ramps to their respective target locations, essentially leveling the terrain. The animation on the left showcases a scenario where all 11 robots are well localized for their task and do not overlap each other's depositions. The right animation showcases a scenario where the robots have large localization errors where they cross each other's paths. However, Marsala allows each robot to build in reaction to their local environment state. Hence, they are inherently coordinated by the environment state, maintaining progress, but may not guarantee completion. In our future work, we want to extend the system by enabling robots to build an abstract user-defined target structure by decomposing it into a series of navigable goals and associated construction parameters for each robot. The robot team is coordinated through the environment state using our proposed architecture in order to guarantee not just progress, but also completion of the task. And with that, I would like to thank everyone for listening, and please let me know if you have any questions.
Is there any question, the audience?
Thank you for the talk. It's really interesting. I've been reading this paper, like the previous versions of this work, and it's all very exciting. The ramp building, where it's like an emergent structure, is very interesting. But have you considered what happens if during construction that ramp falls over, or for some reason, like a robot, I don't know, can't travel up it because it's too steep? What would happen in those scenarios?
So in our physical implementations, we did have constructions where they were either wrong or the smaller parts of the ramps kind of falls over. Like we used bags that were compressible, that when the robots go over, it can get less steep and they have to correct it. But because they react to the environment state, if the slope, if the structure is smaller than what it wants to build, it would react to it and then build it over. But if it's bigger because of some other kind of environmental interactions, then it would just move back, because assuming it has space, and it would try to build a smaller structure to access this new inaccessible structure as a result of other environmental factors. So the idea is, as long as you give it enough space and material, enough space to back up and enough material to deposit, it should be able to, within a determined number of steps, it should be able to go to the target location.
Okay. I have actually one question. So as you mentioned in the beginning of your presentation, in the construction, basically, the robot changed the environment it operates. And I can easily imagine when in construction, when they dig or load something, so it can basically affect the movability of the other robots. Essentially, what I'm asking is there any case in the application scenarios that you consider that you encounter a deadlock, basically kind of a situation that the robot can't move because of the change you made in the environment as a result of other robots' actions?
Yes, that can happen. That's why I kind of said, like, if you have simple rules, that could be deadlocks. But in the scenarios that we showed, for example, in the flat ramp cases, it's going to be hard for some other, because it's essentially leveling the terrain. The robot should be able to go back. In the other scenario, because only the front robot is allowed to deposit, all the robots are behind. That kind of gives a simple way of saying the other robots will not, trap or create a deadlock scenario. But what we're trying to do is, how can we guarantee, progress in more abstract structures, like what we want to do in the future work, and still leverage this intrinsic decentralization? And that's something we are looking into for our future work.
Thank you, Vivek. And let's thank the and conclude the session.